This presentation is about performance calculations, so more FAA test questions, just explaining how to do these test questions. It should be of help to you while you're studying for the dispatcher knowledge test or the airline transport pilot knowledge test. We'll get started with the question that is long. Lots of words are here on this question and lots of numbers given to you. You do not need to know all this information. Here's a question example where they're trying to give you a lot of information and see if you really understand what you are looking for. On this question, it's saying that the airplane is rolling out after touchdown, but that the pilot elects to abort the landing and take off again. They give you some information here about what speed our airplane's at, extraneous information of what our V2 speed is to safely lift off and climb. But then thankfully, they give us an average speed of 129 knots ground speed. One thing you need to memorize here for this type of question is that 1 knot is 1.69 feet per second. That's just a conversion that you're going to need to know. If we look at that average of 129 seconds or 129 knots of ground speed, we also have some other important information on how long the airplane is accelerating. So we have 6 seconds to accelerate, and the engine spooling up to takeoff thrust, it says it's going to take 4 seconds. So here are really the 3 numbers we need, and that 1 knot is 1.67 feet per second conversion. So 1 knot is 1.69 feet per second. That's something you're going to have to memorize. So we can then do 1.69 feet per second times 129 knots, and we get 218 feet per second. Then we can use this 218 feet per second. We can use that to convert us into distance. If we have 218 feet per second and we have 10 seconds, because it said 6 seconds and 4 seconds added together, that would make 10. The seconds, feet per second, the seconds cancel out, and we get 218 feet per second multiplied by 10 seconds. We get 2,180 feet of runway that's actually used in aborting this takeoff. So that was, it's not a hard problem at all, as long as you know that conversion factor. But you do need to know that conversion factor and be able to use that. Moving on to this question, this is a question where we are going to use several different charts. I believe they're for the Q400, and we're going to take a look at that now. So we have several figures to look at. We're given a reported temperature, flap setting, the cowl anti-ice on, and we are given a takeoff weight, and we're instructed to find the VR and the V2 speeds. So first of all, we're going to take a look at figure 342. Here's our airport elevation given to us. We're in St. Augustine in Florida. Airport elevation is only 10 feet above sea level. So basically sea level. Now let's turn over to our figure 451. And we have a chart here where we've got a choice of what column we want to use here. But if we take a look at this, we see the cowl and anti-ice on, PAX on, airport pressure altitude in feet is the left column. And earlier we were told that the cowl anti-ice is on. And we also were given our temperature of negative 10 degrees Celsius. So this is a 2-part question where you have to use this figure 451 to get what's called a reference A. You're going to get a number out of this reference A scale on the right side here. And then we are going to use that and go over to the next page to find the rest of the problem. So on here, we're going to look at the bottom scale, airport outside air temperature in degrees Celsius, and plot a line straight up to sea level, since our airport elevation was about 10 feet. It's basically sea level. And then we're going to draw a line straight over all the way to that reference A scale on the right-hand side, and we get approximately 13.8. That number is really meaningless unless we plug it into the next figure, figure 452, which is on the next page. So we turn the page over here to figure 452, which there's a lot more going on this chart. So let's pause for a moment and take a look at all the things we have to look at here. We have got on the far left a minimum V1, VMCG. Next thing over, we have a scale that allows us to calculate our rotation speed, or VR. And then we have chart A and chart B. So chart A and chart B, we're going to have to determine which chart we actually are going to use to get our V2 speed, because chart A and chart B are both used to calculate a V2 speed. And then there's a note section that we've got, and that note section, again, we always want to make sure to read these notes, look at the chart, figure out what's going on before we just jump into it. So we are going to talk about what those notes are here in a minute. All right, so let's first find our VR. VR is uncomplicated to find from this chart, really. If we start at 13.8 from reference A scale over on the left side, we move over from 13.8 all the way over till we get to a line that references 77,000 pounds. That was given to us in the question. And once we draw that line over to 77,000 pounds, we can then go straight down and we can find a rotation speed of 143 knots for VR. Notice we didn't do anything with the guidelines on that bottom chart because there was no runway slope. If runway slope is 0, you can actually just go straight on down. There's not anything to do with that bottom of that chart if there's no runway slope. So we've got a VR of 143, but this question wanted us to also find the V2 speed. So let's do that now. If we notice, we have notes and it talks about if VR is equal to 1.05 VMCA, don't apply a runway slope correction. Okay, that one, we don't really need to worry about that. If VR is equal to 1.05 VMCA, we're going to obtain V2 from chart A. If VR is greater than 1.05 times VMCA, then we have to use chart B. So we have to first find VMCG, and we have to do that with the left scale. Entering our chart from reference A of 13.8, we draw a line straight over to that reference line for V1, and straight down from there we can find that VMCG is 113 knots. So 113 knots, then multiplying by 1.05 per the notes on the chart, that gives us 119 knots. From before, VR was 143 knots, and so we notice that VR is greater than 119. That means we're going to use chart Bravo. So for chart Bravo, we're going to use our 13.8 reference again. So we draw a line all the way over from the reference line all the way to chart Bravo, and we look for that line that is for 77,000 pounds. And then once we intersect that line, draw straight down from there, and we can find a V2 speed of about 153. Moving on to question 8586. On this one, we are asked to find V1 and VR speed, except for we are actually using a different chart this time. It's actually a less complicated chart. So this is for 25 degrees. We're given sea level, and we are given the airplane's weight. This chart's a little unique in that part of it requires you to go over to the left, which is somewhat backwards when you're doing this type of chart, instead of to the right. So we're going to take a quick look at this chart since it's a little different than maybe what we're used to. What are the V1 and VR speeds for a maximum V1 VR ratio of 0.93? Let's take a look at this. So we have a temperature given to us of 25 degrees Celsius at sea level. Drawing a line up from outside air temperature of 25 degrees Celsius, we intersect at sea level. The scale for this is a little hard to see, so let me indicate it. Here's our altitude for the airfield in thousands of feet. So this line for sea level comes along here, and we draw a line up and intersect it. And then at this point, we can move over, following my blue line, all the way over to the reference line. And then at the point at which we hit the reference line, we begin following these diagonal guidelines. And we follow these guidelines up until we reach the weight of the airplane, which was given to us, 54,500 pounds. And then at 54,500 pounds, we would turn off of those guidelines and keep on proceeding over to the right until we get a VR speed, which is part of what we wanted to know for the question. We can keep going straight over, and at this point we get to a reference line that is all the way over to the right of the chart. And then we have to use that V1 VR ratio of 0.93 that was given to us in the question. So then following backwards from that reference line, we go back down and to the left diagonally till we get to a V1 VR ratio of 0.93. And then on over to the right, and we get a V1 speed of about 101 knots. So in this case, our VR speed, we calculated out to be 109 knots, and we got a V1 speed of about 101 knots. Again, just remembering on this chart, you have to go all the way straight over to that reference line and then backwards to the appropriate V1 VR ratio over down and to the left before heading back over to the right scale to get our V1 scale. And this is just a little comic strip that you might enjoy, and I'll allow you to take a look at that. Hopefully it gives you a bit of humor with all these questions that we've been working on. A reminder to always read the notes. There are a lot of FAA test questions that can be answered incorrectly very easily, and I have seen students do this time and again on tests if they didn't read the notes on the chart. Please watch for this, because there are test questions that are going to try to trick you if you do not read carefully. And this next few questions is going to demonstrate this. Moving on to this question, 8613. On this one, we're talking about a maximum torque for climb that we are supposed to calculate. So, an outside air temperature is given to us of 10 degrees Celsius. The inertial separator is in bypass, and the cabin heater, it actually does not say if the cabin heater is on or off, but since it just says and cabin heater, we are going to assume that it is on, and they want us to calculate the maximum torque for the climb. Read these notes on the chart, and we're going to take a 10 degrees Celsius outside air temperature. We go straight up all the way to the torque limit on the chart, which is 1865 pounds. I am sure that one of the FAA question answers that you may see is 1,865 foot-pounds of torque. If you pick that, you would be wrong. There's no pressure altitude given to us, so we can go up to that 1,865 foot-pound line. That's fine. The guidelines on this chart are just if we had a lower pressure altitude given to us. But we are going to use 1,865. However, Because we have the inertial separator in bypass and the cabin heater, 1865 foot-pounds is not the answer, and you would get that wrong if you chose that for your answer. Per the notes, we have to subtract 100 foot-pounds for that inertial separator being in bypass, and we have to subtract 80 foot-pounds for the cabin heater being on. 1,865 minus 100 minus 80 gives us 1,685 foot-pounds, which is the correct answer. This was a good example of a chart where it's very easy to miss the notes, ignore the notes, and get the answer wrong. We're going to see some more of those coming up. Question 8636. This time, we want to find out the aircraft weight at the top of climb for our operating condition V4. First of all, we need to find our brake release weight for this table. And we see here that our brake release weight for conditions V4, it says 105. And that's in times 1,000 pounds. So 105,000 pounds is our brake release weight. Now we can go into the climb charts and determine which one to use. For conditions V4, we need to use the one for isotemperature plus 10. So a standard atmosphere plus 10. So making sure we're using the correct climb chart, we need the one for plus 10 ISA, and here is the chart. Now we can use our cruise pressure altitude, and we can use some information on here of our brake release weight of 105,000 pounds. We can find the intersection of our brake release weight and our pressure altitude, and we can see here, if we take a look at that top left corner, the units are in minutes, pounds of fuel used, nautical miles climbed, and knots. What we really want to know, remember, we're trying to find the aircraft weight at the top of climb. How would an aircraft lose weight in a climb? Well, the only way is not passengers jumping out, hopefully, but losing the fuel that it's burning as it climbs. We've got our brake release weight, and we just need to determine how many 1,000 pounds of fuel it uses in its climb. Take that number, subtract it from our brake release weight, and we will be able to find the aircraft's weight at the top of climb. Let's continue on and do that. So from here, we see that the airplane has burned 2,400 pounds in its climb. Another thing, though, to notice, for conditions V4, we were told the airport elevation is actually 4,000 feet. And there's a correction table at the bottom of this en route climb chart that tells us if the airport elevation is 4,000 feet, we burned 300 pounds less fuel in the climb since the airplane didn't have to climb as far. So taking our correction, we have 2,400 pounds of fuel burned in the climb. Remove 300 pounds for our airport elevation. That gives us 2,100 pounds of fuel for the climb. But that's not the answer because we need to know our takeoff weight first and take out that fuel used for the climb, since what we want to find out is the aircraft weight at top of climb. So our takeoff weight was 105,000 pounds. We subtract 2,100 pounds and we get an aircraft weight of 102,900 pounds at the top of climb. Again, reading those notes at the bottom and taking a good large overview of the chart, looking at that for as far as the airport elevation and those notes, that's critical to getting these questions right. It's not hard math. It's can you read, can you understand what is going on the chart? Progressing to a little bit more complicated chart, we're going to look at this one. This one instructs us to find the max climb EPR for operating conditions T4. In these operating conditions, we can see that we get a total air temperature, we've got the altitude given to us, and we've got different conditions for engine anti-ice, wing anti-ice, and the air conditioning. And that's going to come into play in our next chart. So read these chart instructions. This is one of these helpful charts where they give you the chart instructions printed on it. You don't need to have memorized how to use this chart. Number one, it tells us to find the temp limit EPR. EPR is engine pressure ratio. So first we're going to find our temp limit EPR. Next step is to find the pressure limit EPR. And then we use the smaller of these two limits. That is where we're going to use any corrections would be applied to the smaller of the two limits. And looking at this, we can see that our temp limit EPR is 2.2. We just take a look at the total air temperature, which was given to us of negative 30 degrees C, and our altitude, which was 35,000 feet. And where those intersect, we see a temp limit EPR of 2.20. So negative 30 degrees, 35,000 feet. Where those two intersect, we see a temp limit EPR of 2.20. All right, that was our temp limit EPR. Now we're going to find our pressure limit EPR. The pressure limit EPR we find to be 2.30. Now we don't interpolate on these. We just find the altitude and we use the EPR number that's above it if it's in that range. So hooray, no interpolating for you. 5,680 feet and above, then our pressure limit EPR is 2.30. Now it's told us to use a smaller of the two limits. Remember, we're reading our chart instructions. So our smaller of those two, 2.2 versus 2.3, obviously smaller is 2.20. Now we've got to take our anti-ice and our air conditioning corrections. So it tells us that the engine anti-ice is on, and our correction given on the chart is minus 0.08. And also we're told that one wing anti-ice is on, one system is on. So we take a correction of subtracting 0.06. The air conditioning is on, so there is no correction to take as far as the air conditioning. I guarantee one of the FAA test question answers is 2.20. They want to see if you're noticing these things on the notes and taking these corrections. So work slow enough and reading the notes enough that you can see what is going on and take those corrections. So our EPR of 2.20, subtract 0.06 and subtract 0.08, and we come up with a max climb engine pressure ratio of 2.06. That's the answer to this question. On this one, we're going to look at another type of chart, how to run this chart. And so first, we've got to look at the airport elevation, because whenever we have, almost always on these type of charts, if they tell us to refer to an instrument approach procedure or an airport diagram, it's because we have an airport elevation to use on the next chart. So paying attention to that. This one's for Gunnison, Colorado, and we're really high up in the mountains here, and we've got an airport elevation that's over a mile high, 7,680 feet. So I'm positive that's going to come into play on my next chart. So here's the chart that we are using that height. We have to use a weight of 69,000 pounds, flaps of 45, with calm winds, and we are instructed to find the VREF. So what's VREF? Well, VREF is the speed that the pilots are going to calculate and fly the airplane on its approach speed. It's basically a variable approach speed for that airplane for that day. It's calculated. The pilots would very, very rarely, or a dispatcher would very, very rarely actually use one of these charts to calculate this, but we have to calculate it for this type of test. Much more likely that it would just be given to the pilots for that day, or even given by the airplane's computers. So looking at this chart, we have a weight of 69,000 pounds and the flaps 45. We have to use the 10,000 foot line because of airport elevation. So we have 5,000 feet and below line, and then another line for 10,000 feet. Our airport elevation was pretty high. So drawing a line up from 69,000 pounds at the bottom, make sure you're using pounds and not kilograms, up to a point between that 5,000 foot and below line and the 10,000 foot line. We can then go straight over and we can get a VREF speed of 136 knots. The next question also involves VREF. But it's really, really important to note that we want to find out VREF plus 20. Sometimes we are going to have to find a VREF speed that is not just VREF, but it'll be VREF plus 10, VREF plus 20. Important to notice that. I've had a lot of students turn in problems and they have it perfectly calculated, but they didn't add the 10 or the 20 knot factor that the question asked them to add. Work slowly, work carefully, and pay attention to what it is you're trying to find and avoid making silly mistakes. We want to find VREF plus 20 for operating conditions L3. This is going to use a different chart for the Boeing 737. Important to add, to find VREF plus 20, we're just going to find VREF and then we're going to add 20 to whatever it is that we get. On this one, we're going to notice also that we're given a runway assignment and we're given a surface wind. So in this VREF calculation, we're going to have to take headwind or crosswind into account. First, let's find out the headwind component. We actually do need to know the headwind component to do this problem. And we have a runway heading of 270, and we are given a wind of 310 for its direction. We're going to find the angle between these two. So 310 and 270, the angle between the two is 40 degrees. Next, we notice that there's 20 knots of wind. So we've got a line on our headwind calculator chart here, and it's 40 degrees off. We can then find the arc for 20 knots of wind, and from that arc, where that intersects with the 40 degree off the runway line, we go over off to the left scale and we can find our wind component parallel to the runway, which, if I'm looking at that, it's about 15 knots of headwind component for this day and this runway assignment. So we're going to note that 15 knots of headwind component is what we found for this problem. Now let's take a look at the actual chart where we can find the VREF. The flap extension and maneuvering speed is shown, as well as landing speed. And reference speed is given to us here, as well as the gross weight. We're actually going to not even pay attention to the flap extension and maneuvering speed chart. We're only going to look at this landing speed chart and the reference speed that's given here. So we're told 90,000 pounds is our gross weight, and we have to find VREF for a flap setting of 15 degrees. So we take a look at this column for 15 degrees and read down to where it intersects with 90,000 pounds and 141 knots. That's VREF. Now, if we use that for our answer, we would be wrong because we have forgotten the note that's right under that that says we're going to add a wind factor of half the headwind component plus gust. This problem did not say anything about gust. And we remembered that our wind factor was 15. Half of that is approximately 8. I would say 7.5 and round it up to 8. Plus 20 knots. Remember that question asked for VREF plus 20. So 141 knots plus 8 knots plus 20 knots for VREF plus 20, and we get 169 knots. And that's the answer to this question. I'm going to look at one further question. This one's simple if you read the notes. They're all relatively simple if you read the notes, and if you follow along, understand what we're doing here. On this, we're going to look at figure 394 and 395, and we're instructed to find the takeoff ground roll for a weight of 8,750 pounds and a pressure altitude of 4,000 feet. Taking a look at this chart, we can see we are given pressure altitude, we're given a few different temperatures, and we can find the ground roll in feet or total distance to clear a 50-foot obstacle. I believe this chart is for a Cessna Caravan, actually. 4,000 foot pressure altitude, and we're also told that our outside air temperature today is 10 degrees Celsius. And so we use this part of the chart for 10 degrees Celsius. And we can read down from there and find that the ground roll, that's what they would like, is 1,760. Simple. We have a little bit of a note here though, because we have to have a wind correction. And the question tells us that there is an 11 knot headwind component, and we need, according to the note, if there's an 11 knot headwind component, we have to decrease the distance by 10%. So 1,760 was what we got for our ground roll. Multiply that by 0.9, and we get 1,584 feet for our ground roll.